So before we start, I just want to say that today's lecture is going to be extremely important because it's going to set the foundation for the application of reinforcement learning in large language models. And we are going to look at a concept today which is at the heart of RL applied to LLMs. So let's get started. I'll start by sharing my screen. Okay, so the topic of today's lecture is policy gradient methods. And we are going to understand about policy gradient methods in complete depth so that you understand all of these algorithms. You might have heard about PPO, GRPO. Uh, all of these algorithms are actually a derivative or based on policy gradient methods. So if you want to understand these algorithms, it is very important for us to first develop a very fundamental understanding of what is the meaning of policy gradient methods. So let's first of all do a small recap of what we have done so far. The question that we have always been interested in reinforcement learning is that if I am in a specific state, then what action should I take in that specific state? And this is told to us by the policy of our agent. So far, what we have been doing is that first thing we looked at was tabular methods. In tabular methods, we create a table where you have states and actions as the first column, and the second column is the Q value. And you keep on populating this table so that your estimates of Q values keep on getting better and better. But the problem is that this method is not scalable. And why it is not scalable? It's because as your states and actions increase, the number of entries in your table also increases. So it is not possible for us to use tabular methods when looking at complex problems like the Atari game simulation, which we looked at in the last lecture. So then how did we modify our approach? Then we said that, okay, fine, let's not do tabular methods anymore. But instead of that, we will construct a neural network such that when given a state, it will predict the Q values for all the actions for that specific state. And the advantage of constructing such a neural network is that you do not have to maintain lengthy tables, but rather now you have a trained neural network which you can use to predict the Q values of the states and actions which your agent has not seen in the past before. So this made representation of large scale systems suddenly possible to us. We could represent complex games, complex environments where there are huge number of states and actions without having to write all the single details in a table. And we looked at a very nice example of this in the last lecture where we learned how to build an agent which can play video games by using the neural network to approximate the Q values. So this is what we looked at in the last lecture. Now we are going to go one step further. The question that we ask is, currently the way we are taking our actions is we are asking the question for every state and action, what is the best Q value? Or for every state, which action has the best Q value? And then you choose to take that action for that specific state. Now we ask the question that can we do something better than this? To give you an analogy, let's say we are in a specific state right now and we want to go to a destination. Let's say I'm going from a city A to a place B in the same city, and there are 5 different actions I can take. Now, whatever we are doing right now is basically we are calculating the time taken from, let's say, point A to point B and we are choosing the path which allows us to get to point B in the best possible time if that's the reward we want to optimize. But we are not directly answering the question, which path should I take? Now the question we are asking is that given a state, can I directly get the probability distribution for all possible actions without going through the Q value? So Q value is almost like something which we have based our policy based on the Q value. But you might ask the question that why is this Q value required? Why can't I directly get my policy? Why can't I get a probability distribution for every state which looks something like this? Let's say I'm in a specific state and there are three possible actions, and the probability distribution looks like this. This is 0.3 and this is 0.8, let's say. And this is A1, A2, and A3. So I can clearly take action A2 for this specific state because the probability is the highest. Or rather, I take action A2 with a probability of 0.8, and then I take other actions with a less probability. So in today's lecture, we are going to look at a class of methods which completely bypass the need to calculate the Q values, and they can directly give you the probability distribution for every state. And this is extremely efficient in terms of implementing reinforcement learning problems for large scale systems because it directly allows us to estimate the policy without going through the intermediate Q value function in between. And these class of methods are called as policy gradient methods. So let's try to understand them in detail. So far we have looked at action value function and asked the question for every state, which action is giving me the maximum Q value. Now what we'll be doing is that we are going to learn an optimal policy without considering the value function at all. So my objective is going to be to estimate pi of A given S, which means what is the probability of taking a specific action if the agent is inside a specific state or if the agent has collected a specific observation from the environment. And this is going to be denoted as pi of A given S. And we are also going to introduce a parameter theta, which is called as the policy parameter. So this is how we are going to write our policy, pi of A given S comma theta, because our policy is dependent on the policy parameter theta. Now let's take a deeper look into what exactly does it mean to have a policy parameter. Let's construct a hypothetical example. Let's say we have a state S and there are 5 possible actions in the state. And these actions are denoted by A1, A2, A3, A4, and A5. And on the right hand side, we write down the numerical preferences for these actions. So A1 has a numerical preference of 3, A2 has 2, A3 4, A4 5, and A5 is the most preferred action, which has the preference of 1. Now my objective is to convert these preferences into a policy representation using a policy parameter theta. So let's see how we can do it. Some of you already might have some intuition about this if you have learnt about the softmax function before, but if not, I'm going to explain that again right now. So first of all, let's try to capture this through some kind of a polynomial. Let's say we capture it through this polynomial. So you can see that this polynomial perfectly goes through my data. For action 1, the preference is 3. For action 2, the preference is 2. And for action 5, the preference is 1. So this function can be written as theta 0 plus C1 theta plus C2 theta square, let's say. And we have estimated this C1 and C2 so as to fit this data. So this is an example of a function which we have parameterized with a parameter theta. Theta can also be thought of as weights in a as you as you say, when you think about neural networks, you have weights which are denoted by W. Theta is a parameter which is tunable. I can tune theta, consider it sort of like a knob. I can rotate my knob so as to move my policy up or down, or to squeeze my policy or expand my policy. So theta is a parameter which we are going to parameterize our policy with. Now the problem with this H is that it is not giving me probabilities. It still gives me the numbers as an output, which is not what I want. I want to convert these preferences into probability estimates between 0 to 1. And the way that is done is we use a softmax function. So in the softmax function, what we do is, let's say we want to convert the preference 3 into a probability. So we do e raised to 3 divided by addition of all the exponents. So e raised to 3 plus e raised to 2 plus e raised to 4 plus e raised to 5 plus e raised to 1. This is how I will change my preference to a probability, because this will lie between 0 and 1 always. So this is called as the softmax function, and we convert individual preferences into probabilities. And if you do that for all the preferences, you will see a distribution like this. Now, this is an example of a parameterized policy. Why is it an example of a policy? Because it gives me a probability for all the actions. Why parameterized? Because this policy is determined only as a function of theta. So this is what we want to achieve in today's lecture. Given an agent, given an environment, given a set of states and actions, we want to calculate a policy which looks something like this, which directly allows us to estimate the probability of all possible actions for a given state. So this kind of representation is called softmax of numerical preferences. In reality, the numerical preferences will not be given to you, because you will be leaving an agent in an environment, collecting experiences and building this policy by yourself. But I included this in the discussion because I wanted to give you an idea of what does a parameterized policy really look like, and how can it be constructed from preferences in general. Okay, so now we want to calculate this policy. The main question is that how do we find this kind of a policy? How do we find a policy parameter which can give me the best possible policy so that I maximize my reward, right? And this is the same question which researchers faced in the late 80s, early 90s, where policy gradient field was still very much at the nascent stages. And to answer this question, people said that, okay, you want to find the parameter theta in your policy, or you want to optimize the parameters of your policy to achieve some performance measure, right? So then people started to think from that point of view that, okay, what is the performance measure that I want to optimize? So let's say hypothetically we have a performance measure which is defined as j of theta. Right now we don't know what this is, but imagine that we have a performance measure j of theta. And the question that we ask is, okay, so if we know how to calculate this performance measure, let's say the performance measure looks something like this. And on the x-axis you have theta, on the y-axis you have j of theta. And let's say this is your current theta, which is theta naught. Then we have a mechanism in place to find the best theta. How you are going to do that? You are simply going to ascend this mountain so that you slowly reach the peak of this mountain. And this you are going to do by using this update rule, theta t plus 1 equal to theta t plus alpha times grad of j of theta. So in traditional machine learning algorithms, you're trying to minimize your loss. So you will see a negative sign over here, but here we want to maximize our performance measure. So This is an example of a gradient ascent algorithm where we are ascending the mountain to reach its peak. So first we'll do theta 1 equal to theta 0 plus alpha times gradient of j of theta evaluated at theta equal to theta of 0. And then slowly we are going to do this many times so that we do better and better and better. So people intuitively knew the strategy that, okay, fine, if we know what this performance measure is, we can ascend this that makes sense. So now this is how the gradient ascent on the performance measure schematically looks like. We start from point A and we want to move on the surface to reach point B. The biggest problem with this method is that right now I have shown you a surface which we can navigate, right? But if you look at reinforcement learning problems, it's not easy to find derivative of the performance measure. And because the derivative depends on a lot of things, it's not as easy to ascend this mountain. So even though theoretically it sounds like we have a plan, but we are going to be getting stuck in this step, which is grad of j of theta. How do I calculate that? So before we do that, first let's understand how this performance measure is defined by. The performance measure is defined in a very simple way. It's defined as the value function of the initial state of the episode. So it's defined as V pi of S0. Why is this the performance measure? Remember when we started discussing about reinforcement learning agent environment interface, we discussed that the sole aim of the reinforcement learning agent is to maximize the cumulative rewards which the agent receives in the long run from the start to the end of the episode. And this is nothing but what the value function measures. The value function, the definition of the value function is expected returns which the agent is supposed to accumulate from the initial state to the end of the episode. So that's the reason we define the performance measure by the value function at the start of the episode, which is V pi of S0. So that's great. The performance function is defined. Now we want to look at how can we calculate the gradient of this performance measure, which is the biggest bottleneck in this whole process. And the reason why it's not easy is because the performance of a policy depends on two things. It depends on which states you are visiting in a trajectory and what kind of actions you are taking in that state. So calculating the gradient of the performance measure was a challenging task. But in the year 1999, there were two parallel papers which came out. 1999. One was from Richard Sutton Group, and the another one, I don't recall the name right now. So one paper was a 12-page long proof, and one paper was a one-page long proof. And both of them arrived at the same conclusion. And this is known as the policy gradient theorem. And the policy gradient theorem gives us a very nice formula to calculate the gradient of this performance measure. So what I'm going to do right now is I'm going to do this derivation, and I have distilled this derivation down in a series of just 7 steps so that all of you can understand. But we have to go through this derivation because it is at the heart of what we are going, or where the path we are going from this lecture towards GRPO PPO. To navigate that path properly, we need to understand this derivation. And we are going to take a very easy look at this derivation. Okay, so here I am going to start with the derivation. So firstly, let's look at j of theta. So j of theta is nothing but value function of S0 if I follow a specific policy pi. Now, this value function can be written as expected value of g of tau. Tau is one single trajectory and g is the return. And this expectation we are going to take across all possible trajectories. So what this means is that you sample a lot of trajectories and calculate the return G for all these trajectories and then take an average of all those returns. So the first step, which is step number 1, is where we say grad of J of theta is equal to grad of expected value of G of tau, where tau is sampled from the policy itself. Okay, so this step is just we have substituted the formula. Now in step number 2, what we are going to do is we are going to expand the expectation. So step number 2, we are going to say that grad of J of theta is equal to grad of summation of probability of that trajectory being sampled times return from the trajectory. So this is a standard formula for expectation of any variable. If let's say you're throwing a dice and you want to find the expectation of that action or that event, you find the probability of each, let's say the probability of the top side being 1 is 1 by 6. So 1 by 6 into uh, the face value, which is 1, plus 1 by 6 into the face value, that is 2. So you get the expected value of the face value of the dice. So what you basically do is you rewrite this expectation as probability of that trajectory being sampled times the return you get from that trajectory. So this is comes from the definition of expectation. Now, step number 3, all of us have learned in preliminary calculus that the gradient of summation is equal to the summation of gradients. So we are just going to take this integral or this gradient inside the integral. So it's going to be equal to grad of or integral grad of P of tau given theta times G of tau. Okay, so far so good. Now we are going to do one trick, and that trick is called as the log derivative trick. So what I'm going to do is I'm going to say grad of J of theta is equal to integral, write this with a different color, P of tau comma tau given theta multiplied by gradient of log of P of tau given theta times G of tau. Now, how is this equivalent to this? Let me give a simple example of that. So let's say we have P of x here. So gradient of P of x and gradient of log P of x into P of x. Now gradient of log can be written as 1 upon P of x into gradient of P of x. So this P of x cancels and you finally get this one only. So it's just a simple trick to write this derivation as multiplication of this into grad of log of this. Okay, so far we have not done anything complicated. Now what we do is we take this back to the expectation form. So if we take back to expectation form, we'll get something like this. Expectation of the probability will not come because we are taking an expectation now. Grad of log P of tau given theta into G of tau. And this expectation is taken over all trajectories. Okay, so this is step, this should be step 5. So we are almost there. We only have 7 steps in this process. So step 4, step 5. So far what we have done is we have said that gradient of G of theta is equal to expectation over all possible trajectories. Grad of log probability of that trajectory times g of tau. Okay. Now what we are going to do is, this step is the most important, and after that we are directly going to get to the answer. So please pay a very close attention to this step, and this is the only complicated step or slightly complicated step in this derivation. We are going to expand this now. Probability of tau given theta. Remember, tau is the original trajectory. So I am going to expand this probability of tau given theta as probability of the initial state, which is the S0 starting state, which I am calling as rho 0. And then this pi denotes that I am going to multiply whatever is coming inside. Probability of st plus 1 given st comma at times pi of at given st. So what does this mean? How come this has transformed to this? Okay, so let's start from the first. First, I take the probability of starting out at state S0. Then I do what's the probability that I take action AT. So I multiply by that, and then I again multiply that by the transition probability from state S0 to S1. So this pi simply means that we are multiplying probability of S1 given S0, comma A0 into probability of S2 given S1, comma A1. So essentially we are writing down the probability of the entire trajectory in terms of the series. So initially we have S0, then we go to S1, S2, S3, etc. So we are multiplying all of this in this expression. Now, here what we have to do is we have to take grad of log of this. So let's understand. So grad of log of p of tau given theta is going to be grad of log of all these terms. Now, log of a into b can be written as log of a plus log of b. And we are going to use that same expression here. We are going to split these terms, and that's what log allows us to do. So we are going to write this as grad of log of rho 0 S0 plus sigma t goes from 0 to t, grad of log p st plus 1 given st comma at plus sigma t goes from 0 to t, grad of log pi at given st. So we have simply divided the gradient into three terms. Now the best part comes here. This term does not depend on theta. This term does not depend on theta, because we are simply taking a gradient of probability of st plus 1 given st comma at. There is no theta coming here. So this cancels out. This also cancels out. And we get a very simple expression for the gradient, which looks like this. Grad log probability of tau given theta is nothing but summation over the, for t goes from 0 to the last state, grad of log of pi at given st. What does this mean? This means that we first have to calculate the log of the policy, take the gradient of that, and then sum it up for all the states in the episode. And now we substitute this here to get our final expression, which we'll write as step number 7. And this is all that we need to understand everything in this lecture. Grad of j of theta is equal to expectation over all possible trajectories. And what are we sampling from? So we are sampling this summation over all the states, gradient of log probabilities and this G is also there, remember. So G of tau. That's it. So this is one formula which, because of this policy gradients, calculating the gradient of the performance measure suddenly became possible. And the entire field really bloomed after this proof was, after this proof really came out. So I'll delete this. Okay, so this is the final formula which we are going to look at. Let us again understand what's happening in this formula. This formula is saying that if you want to calculate the gradient of the performance measure of the policy, you first have to sample a lot of trajectories. And let's look at one specific trajectory which you have sampled. For that specific trajectory, you add up the gradient of the log probabilities for all the actions and multiply it by the return received at the end of the episode. So there are two terms here. One is simple, it's the return which our agent is getting at the end of the episode. But the more important term, which you will see appear again and again in a lot of papers, is this term, which is called as the grad log probabilities. Okay, so this is what is the main term which is given to us by our policy gradient theorem. And this was one of the main game changers which really brought this field to the prominence. Okay, so now that, okay, we have got some idea of what the policy gradient theorem is, what we will do is we'll try to build an intuition for this policy gradient theorem. What exactly does the policy gradient theorem mean? So it's very important for us to understand the intuition. Otherwise, we'll just be people who look at formulas, derive them, and just then sit at home. But we are not really understanding what's happening with all these terms. So let's take a simple example. So let's say your old policy is this. It's given by some combination of theta1 and theta2. Let's say you have two parameters which you have used to parameterize your policy. And then you take an action AT in the environment and from a state ST. And now your policy update direction is given by grad of log pi. So this term, which is gradient of log of the policy, is telling you in which direction should you move to get the new policy. And what this intuitively means is that, let's say you sample from a specific trajectory and you are looking at one particular state and you are looking at the action taken from that state. Now, if you receive a very bad reward for that action, it means that your policy is going to decrease the probability of taking that action from that state S whenever later that agent encounters the state S. And this you can see very nicely from this diagram. So if the G sign is positive, if G is positive, it means that I am traversing up this mountain. And this mountain is nothing but pi of AT given ST, which means the probability of taking action AT when in state ST. So higher values means that that action is preferred more, and lower values means that the action is not preferred that much. So if G is positive, I am going to move up this mountain like this. And if G is negative, I am going to move down this mountain, which intuitively makes a lot of sense, right? If G is positive, you want to reinforce that action. You want to increase the probability of taking action AT when encountered in ST. And if G is negative, you want to penalize that action. So whether you want to reinforce or penalize is captured very nicely by this G. If it's positive, it reinforces. If it's negative, it penalizes. So that's the main intuition. And the direction is given by this. So you can, once you know that you want to traverse towards the peak, you can go in any direction, right? But grad of log pi essentially gives you how to navigate through the mountain so that you reach towards the peak of the mountain. And this is exactly what the gradient of the performance measure tells us. It gives us a direction to move to reinforce good actions and penalize bad actions. That is what I want to you to understand. um, what is the main essence of the gradient measure, the gradient of the performance measure. Now that we have obtained the gradient of the performance measure, now we can simply go ahead and I will refer to this notes which I have written over here. So now that we have obtained this formula, which is the gradient of the performance measure, we can now use this formula inside our gradient ascent algorithm to write down a policy update rule. So the policy update rule then looks as follows. Okay, so that I have not written here, but let me write it down. Policy update rule essentially looks like theta t plus 1 equal to theta t plus alpha times this entire expression. Grad of summation is missing. Summation t goes from 0 to t log grad log pi at given st times g of t. This is the policy update rule through which we'll update our policy of the agent. And this is exactly what was the first algorithm proposed. It was called as the reinforce algorithm. And probably why the name reinforce comes is because this algorithm reinforces good actions and penalizes bad actions. And now you can understand this formula, right? This is the exact same formula which we have derived in class. So this is the first policy gradient algorithm which I think came out in 92, which was the reinforce algorithm. And we do not need to rely on the q values for this specific algorithm. All we need to rely on is we directly get the policy after you apply this gradient ascent rule. And this is the first time that we are going to uh, use or directly update the weights of our policy so that our policy gets better and better and better. Okay, so this is the first algorithm, reinforce algorithm. At the backbone of this algorithm is the proof for the gradient of the performance measure. Now, let's try to understand some of the issues which happened with reinforce algorithm. Although it gave a very elegant expression for calculating uh, the gradient of the performance measure, the main problem with reinforce algorithm is that of variance. Look at this here. We are taking the expectation over all possible trajectories, right? And this is exactly what is the root cause of the problem. So imagine that you want to find out the average age of your country, and you go ahead and collect a lot of samples and find out the average. So your estimate is going to heavily depend on the people you collected the samples from. For example, if you only sample people above 60 years of age, you will wrongly think that the average age of the country is more than 60. If you sample people who are only less than 20 years of age, then again you will have a wrong estimate. So in this figure, I have shown different sampling strategies which can induce a lot of uh, differences in our predictions. For example, the true population is shown somewhere at the back. You can see these small blue bars. That is the true population. But all of my samples are predicting something else because these are finally samples. They are not giving you the actual true distribution. And because of the here also we are sampling so many times, but if there are 1,000 trajectories and we only sample 20 or 30 of them, every time I'm sampling one trajectory, my variance is going on increasing, right? I'm not converging to a value. And that is one of the main issues with the reinforced algorithm. And this variance usually comes out because of this G term here. For every trajectory which I sample, the return which I get is different. And these have huge difference in magnitudes. For example, one return can be 2, the second return can be 2000. So one single return can dramatically influence your estimates for the gradients. And because of this, the reinforced algorithm was not very effective in estimating these gradients, because it sometimes used to lead to a lot of variance in the data. And then people started to think, how do I take care of this variance problem? Is there a way I can subtly modify this reinforced algorithm so that I take care of the gradients? And the way people did that is, so let me just a second. Okay. Okay, my pen has stopped working, so maybe I'll just explain this. Okay, now it's working again. Okay, maybe I'll explain this concept through text initially. So, what happens in reinforce with baseline is that, so reinforce with baseline is the modified reinforce method which people came up with to solve the variance problem. In the reinforce with baseline method, a constant value is subtracted from the return, and this constant value depends on the state. So, as you can see from the expression here, everything else stays exactly the same as per the reinforced algorithm, but there is another term here which says minus b of s, which is the baseline which we are subtracting from the return. So you can consider this baseline sort of like a normalization trick. If you have values like 2, 2000, 200, etc. in your measurements, and if you subtract the mean from the values, you are going to get normalized values, which are going to reduce your variance. So introducing a baseline was kind of similar. It preserves the proof of the gradient of the performance measure, because the baseline does not depend on the actions, it only depends on the states. But at the same time, it helps a lot in reducing variance. And then this small change uh, created a lot of difference. Another change which people did to reduce variance is, here you can see I have written g of tau, which means the return which the agent receives at the end of the episode. People replace that by g of t itself, which is the return received from that state till the end of the episode. So there were two main changes which were done to transition from the reinforce method to the reinforce with baseline. The first change was that a constant term was subtracted, and then the second change was that tau was replaced by t. So how the baseline is decided is something I have not explained right now, but I will be explaining it eventually. But you can just understand for now, the purpose of baseline is to uh, help our model understand that don't focus too much on returns which are giving you very high values unnecessarily, but try to focus on actions which are leading to good returns without focusing too much on the magnitude. And that's why we subtract this b of s from the return, so that we get a variance curve which is stabilized. So far, we have not seen whether this actually works. In today's lecture, we are going to see a proof of how the reinforce with baseline works and why it's considered to be more effective as compared to the simple reinforce algorithm. Now let's go back to our notes and we'll try to understand this. So this is how the reinforce with baseline algorithm is modified. Up until now, everything is the same, but here you have gt minus b of s. Now, what people usually do is that this b of s is replaced with value function as the baseline. And this is in fact an extremely common usage. You will see this in a lot of algorithms that we will look at later. And I would say in most of the examples I have seen in literature and the ones I have implemented, the baseline is always the value function. In some cases, the baseline can be the mean of all the rewards that you get in the episode, for example. So you can construct the baseline by yourself, but a very popular baseline is called as is just the value function v of s. So the final expression when you write it as g of t minus v of s. And this sort of method or this sort of formulation is also called as the actor-critic formulation. And I have always been surprised by how this name comes about. What is the actor and what is the critic? So what I've come to understand after some deliberation is that the one that you're subtracting, this is the critic. And the one that you're subtracting from is the actor. So the critique is something like a judge, where you are judging whether the actor is uh, performing well or not. It's like kind of something which, if the actor is moving too astray or is having very large value, then the critique brings it back towards a reasonable value, something like that. Apart from this intuition, there is not really a specific intuition which people have used to call it as actor critic methods. I think it comes from some sort of a teaching algorithm like distillation or something where there is an actor and there is a critique. But in reinforcement learning literature, whenever you see actor and critique, you will read a papers about GRPO after this bootcamp is over. So whenever you see critique, more than 95-99% of the time, the critique will always be the value function. I haven't seen any other critique used in the literature. And this actor, which I am calling G of t, this is also this is actually exactly same as Q of t, which is the action value function. So the actor is the action value function and the critique is the state value function. This is how the reinforcement learning is modified from the original form, the way it was derived, to how it is used in some of the modern implementations. We are going to look at both the methods, reinforce with baseline, and some practical applications so that you understand this in depth. I think let's go ahead and do that for now, and we'll understand the remainder theory after that part is over. So right now, what we are going to do is that we are going to solve a very practical problem with the help of policy gradient methods. And the problem which I have chosen for this is the CartPole problem. So the CartPole problem is a standard problem. Let me show you what it looks like. So it's like you have a cart pole and something like this, let's say, and you have to move the cart pole. Maybe this GIF will make it clear. Yeah. So you have to move this cart pole left and right so that it doesn't fall. If you always move it towards the right, it will eventually fall to the left. If you move it towards the left, it will eventually fall to the right because of gravity. So for every state in the cart pole problem, there are only two actions. First action is whether to move the cart pole to the left, or the second action is whether to move the cart pole to the right. Okay, so there are basically two actions for the cart pole environment. And what are the states? The states are going to be four observations. Okay, so let me just visually explain this. Somehow my pen is doing some weird things, so my handwriting will not be good for this section, but okay, it's fine. So this is the y and the x axis. Okay, so we are going to use four state variables for this problem. The first variable is going to be x, comma x dot, and the second variable is the third and fourth is going to be theta and theta dot, which is the position and the linear velocity of the cart and the angle and the angular velocity of this cart. So these are the four observation or the state values which I'm going to receive. So the state is going to be a vector of four values, and the actions is going to be just either 0 or 1, which is left or right. And my objective is to uh, create a policy which can allow me to stabilize or move this cart in a way such that the cart does not fall over. So that is my main objective. Okay, so now let's start to understand how I'm going to start thinking of this problem. Before we start looking at the code, let's first try to understand the logic which I'm going to implement. So the logic I'm going to implement is, you can see on the left is just my figure or the schematic of the problem, which is the cart pull problem. Step number one is to simulate a bunch of episodes and to collect the states, actions, and rewards. So initially, I'm going to uh, select or initialize the weights of my neural network in a very arbitrary fashion. So there will be random weights. So the actions which my agent is taking, the actions will also be completely random. And then, so initially I'll collect some observations which will probably be very bad because my agent is not yet trained. And then I will use all that information to calculate the Q values or the G values and the grad log probabilities. After this is calculated, I am in a very good position to calculate the gradient of the performance measure because it depends on only two things, the grad log probabilities and the Q values. Once the gradient is calculated, I am going to update my parameters using the gradient ascent rule. And then I'm going to again simulate a bunch of episodes, again collect state action rewards, again calculate grad log probabilities, Q values, again do the gradient ascent. So I'm going to continue this a number of times. So I want you to understand this workflow very nicely because this is the same workflow which we are going to use for a number of different problems which we are going to look at in future, even the language modeling problems which we will look at. So the main workflow here is you basically have an agent environment interface on the left here. Then you collect a lot of trajectories. So this is the terminology I'm going to use in the future is you simulate a lot of trajectories. Okay, then update your neural network, again simulate a lot of trajectories, again update your neural network. So you are going to keep on doing this a number of times. So this is quite different than traditional machine learning problems where the data set is available to us and then we just perform training. Now here what we are doing is we are performing training, generating data set, then performing training, again generating data set. So there are two steps involved in this whole process. The first step is generating the data set or the trajectories, and the second step is actually training your neural network. Okay, so I hope this part is clear for all of you. And now we are going to look at some code snippets so that you understand how these codes are written. And these are very short codes, they are not very big, but uh, all the code files, they follow this same workflow which I'm explaining to all of you right now. Okay, so let me go ahead and open it up. Okay, that's something different. Okay, so we are going to look at different pieces of our code so that we understand them better. The first question which all of you might have is, what is the architecture of my neural network? How am I defining the neural network? So this is a neural network which has just three layers. It has an input layer, it has a hidden layer, and it has an output layer. Okay, so there are three layers in this neural network. We Okay, so this is the first layer which transforms from the input layer to the hidden layer. Then there is the ReLU activation function, and then from the hidden layer we map it to the actions of my network. Okay, so I'll just maybe highlight it in a different color so that you're able to understand it. So this is the input to hidden transformation, and this is the hidden to the action transformation. So it's a simple neural network which we are going to work with an input layer, hidden layer, and output layer. Then the next question is, how do we define the function to calculate Q values? And this is a very important step. I want all of you to understand how this Q value calculation is done. Why do we need the Q values? If you remember the gradient of performance measure, we have the log probabilities, log grad probabilities multiplied by the Q values. So I have constructed an example here to help you understand that. Imagine this is the trajectory which my agent is following, right? So the way the Q values are calculated is, first the Q value of the last state is calculated, which is this state number 5, where I get a reward of R5. So the Q value is stored in Q5. So we are starting from the reverse, from the last step of the episode. Then we move to this state, which is Q4, and the Q value is given by R4 plus gamma times R5, which is addition of the immediate reward plus the discounted value of the next reward, which we already know, we have calculated in the previous step. Now what we are doing for Q3 is we are doing R3 plus the discounted value of the next reward plus the discounted value, which is gamma square. Now R4 and R5 are already known from the previous two steps, so all we need to do is add the reward. So this makes the Q value calculation very easy for all the states which are encountered in that specific trajectory. And that is exactly what is done in this function. Let me share this file with all of you so that you can follow along as I am explaining it. Okay. Yeah, just look at this document. So here what we are doing is, you can see first the reward is 0. So the initial sum R, which is going to be just the reward which the agent receives in the first or in the last state, and then the reward is going to be added. Okay, so the last state, because this sum R is initially 0, sum r is equal to r plus sum r. So r is just the last reward, which was r5 in the last example. And then the previous will be r4 plus gamma times r5, and this gamma is multiplied here. So what this entire code ensures is that it ensures that the Q values are properly calculated and stored in an array, which we will be using later for estimating or calculating the gradient of the performance measure. Now the next step is to collect the states, actions, and rewards. Remember here, I mentioned that one of the step is to collect states, actions, and reward, which is the trajectories. This is exactly what we are doing here. So, okay, so first we pass the states through the neural network and we collect the logits, which are the action probabilities. Then what we do is we take the action based on the action. So then we first convert to probabilities by using a softmax layer. And then we pass it to a torch.multinomial, which basically selects the action based on the probability distribution. For example, if the probability distribution is, if there are only two actions, and the first action has a probability of 0.8 and the second action has a probability of 0.2, then the first action will be 4 times as likely to be sampled compared to the second action. So this is ensured in this step. Now we take a step in the environment. This is the famous env.step function, which I have iterated multiple times from the initial first two sessions also. So you pass this action to this env.step and you collect the next state, the reward, and flags whether the episode is done or episode is truncated. So you can see now this entire experience is available to me. I can simulate an entire trajectory because I know a step, I take another step. Uh, First, I know the state, then I calculate the action using my neural network. Then I get to the next state. I again do the same thing and I keep on doing this until I reach the end of the episode. So this is done multiple times in the loop so that you can simulate an entire trajectory. And there are multiple trajectories like these which are simulated, which you will find once I will share the code file with you. But this logic is the most important because if you understand what is happening for one single state, you can understand what is happening for the entire episode. And then you can understand what is happening for multiple trajectories. So this is the main logic which we are implementing. Now, once we have calculated the batches and the states action rewards are collected, now the time comes to calculate the loss and then do this gradient ascent rule. So how that is done is very interesting. So here you see first, we collect the logits for the states and then again do the softmax so that we get the log probabilities. Now remember in this formula, there is log of pi of 80 given st. So pi of 80 given st is going to be the output which my neural network is giving to me. Applied a softmax layer on top of it. And then we have to take a log separately, which is what is being done here. We are doing a log softmax, which calculates softmax and then takes a log. Now, the log probabilities are only taken for the actions that we have taken, not for all the possible actions from that given state, but only for the actions which were taken in that episode. And we know which actions were taken in the episode because we are storing it from the above here. We are storing the action here in these batches, batch.actions.append. So we know which actions were taken. And now once we know that, then you can see the policy loss is simply given by minus. So this minus sign I will explain, but Q vals into T, this is the Q value multiplied by log probabilities, which is exactly same that we have doing here. Q value multiplied by log probabilities. So Q value multiplied by log probabilities here. So whatever you see in this expression over here, it's exactly the same as here. And this is the loss that we will calculate the gradient of and we will back propagate. All that is taken care in this loss dot backward and optimizer dot step function. But here I just want to explain to you how the loss is calculated and how it exactly matches the formula which we have been discussing. And this is something which you will see the same function is repeated for reinforce with baseline as well. The only difference that happens in reinforcement or reinforce with baseline is that this function stays the same, everything else stays the same. The four steps that we had discussed, collecting the trajectories, then finding the log probs, the Q values, then updating via the gradient descent, all that remains the same. But only difference is here in the last step, there is a so I think I have not added it in this file, but I'll show you in the code file right now where that is located. So if you see, this is the function where up until here everything is the same, but I'm subtracting q minus mean q, which is the baseline. Now ideally we should subtract the value function, but we do not know the value function, and in practice the value function also is constructed as a separate neural network, which we will talk about later in some of the other problems that we will consider. But right now, we are using a very simple baseline where we are calculating the average of all the Q values which have been received in a single episode. For example, if you consider this as an example, this trajectory, then okay, first of all, this is the grad of j of theta, which is being calculated in this. So before we get to reinforce with baseline, what we are doing is we are calculating the log of pi of a1 given s1 into g1 plus log of pi a2 given s2 into g2 plus log of pi a3 given s3 into g3, etc. And we do it for all the states encountered in the episode. Now with reinforcement or reinforce with baseline, the baseline that we have constructed is we are calculating the Q values for all of this and taking a mean of them. So it's basically Q1 plus Q2 plus Q3 plus Q4 plus Q5 plus Q6 divided by 6. And that is what is used as the baseline. So what we'll do is let us understand how this code works in practice so that all of you will get uh, the satisfaction of implementing the first policy gradient algorithms by yourself. So this is the repo that we have been referring to. And I want you to again go to this repo and use this or clone this specific folder. And we are going to run both these files separately. First, we are only going to run the reinforce method, and second, we are going to run reinforce with baseline. So let's look at how to run both these codes. So this is where I have my code file which is written for reinforce, the simple reinforce method. Here you can see the same blocks are used. This is the neural network block. This is the Q value calculation block, and this is the block where we calculate the loss. That's it. The rest of the things are all defining loops and making sure that the values are updated in the functions properly. Now, once you have copied this code, you can just simply run this code and then see what's the output you are getting. So do cartpole underscore reinforce.py, and you can see how the rewards change with time. So this is the last run which I was running today morning, but right now let's see. So till the time my output is showing up, why don't all of you copy this code and then run this by yourself? I don't think you will need any extra dependencies because the previous in the previous codes we have already installed the dependencies of Gymnasium, TensorBoard, etc. Yeah, so now you can see the rewards have started coming in, and keep an eye out for this mean reward which is shown on the right. It always goes on increasing, which means that our agent is indeed learning and we are learning to balance the cart for the maximum time so that the pole does not fall over. which is amazing. Only through experience we are learning this. Remember, we don't know any physics of the cart. So slowly it continues. I'll show you some curves which I have got in the past so that will help you understand. But now you can see the rewards. Okay, so I have stopped it because the reward has reached a mean value of 450, which was the condition or the constraint I have given in the code for it to stop. And then also go ahead and run this reinforce with the baseline. And here you can see already that there is a lot of variation between different episodes. It's like it goes up, goes down, and then sometimes it goes too down, again goes up, again goes down. So you can see that there is a lot of variation. But if you run reinforce underscore baseline, first of all, you can see that the output might converge in a less amount of time, or less number of episodes compared to the simple reinforce. So here it converged in 1,70,000 episodes for me, and the previous, let's see, this took 2,57,000. So the reason it converges faster is because of the baseline that we have introduced. And now let's try to visualize this on TensorBoard. So let's see. Okay, so once you run the TensorBoard and just open it up, and let's compare both the curves. So these are the episodes, and you can see that the blue curve, which is reinforced with baseline, it uses far lesser episodes compared to the blue curve. But then let's first understand the reward. The reward dynamics are very interesting. Both of So here you can see the reinforced without baseline, which is the dark blue curve. It behaves very erratically, goes up, goes down again. So you can already see the huge amount of variance, right? So many fluctuations I can see in the data. But then for the light blue, there are not that many fluctuations. There are fluctuations, but definitely way less compared to. And then this is the reward which is averaged across 100 runs. And here you can get to see the Q values. So which is the variance of the Q value. So the light blue, you can see the variance doesn't fluctuate that much. It is almost either way below 600 or at par with 600. But with the blue curve, the variance keeps on oscillating, and at some point it has a very high value also. So the highest peak of the variance of the dark blue is definitely larger than the variance peak which we see with the light blue curve. So this is the kind of results that you should get when you run these algorithms or these policy gradient methods for the CartPole problem. And this again goes to show that we have now looked at two classes of methods. The first is tabular methods, and then we looked at function approximation methods using Q-learning. But today we have opened the door to a whole new class of methods where you don't need to estimate Q values separately, but you directly estimate the policy as a neural network. So this is amazing that the agent is just learning through a bunch of experiences. Now, as I mentioned before, the baseline, which is so Kiran is asking, how do I get on TensorBoard? So for TensorBoard, uh, once you have ran on Google Colab, it might have created a folder called runs locally. So you need to access that folder and use that command TensorBoard directory runs so that it will run separately. Now, in reinforcement with baseline or reinforce, I'm again saying reinforcement. Reinforce with baseline, there is a value function subtracted from the baseline. And the in this example, we have approximated that value function with a mean of Q, which is a crude approximation. But in reality, we need to this g of tau or g of t minus v of t has to be estimated. And let's try to understand how to estimate that. So that brings us to a very important concept in today's lecture, which is called as advantage function. So first, let us understand advantage function from a mathematical point of view. Advantage function is simply given by the difference between the action value function and the state value function. So it is denoted by q pi of st comma at, which is this term, minus v pi of st, which is this term. And this is exactly the term that we get in our reinforce with baseline method. You can see here. So sometimes what people do, and you might see this in literature also, so don't get confused by it. They replace this entire block. They replace this entire block with a of t, where a is called as the advantage. So they don't write g of t and v of s separately, but that entire block is represented by a of t, which is the advantage function. So you might see a lot of books or in papers that this g of tau is replaced by a of t. So you shouldn't be confused at what this a is and how is it, where is it coming from. So this a is called as the advantage. And the intuition behind this advantage is it's really telling us whether or not the action is worse than the policy's default behavior. So let's try to understand this with a simple example. Let's consider a case where there are there is one specific state and there are four values in that state. So let's say we have a state S, and so we have these values A1, A2, A3, and A4. Okay, so there are four possible actions which I can take from this specific state. Now, I am interested to calculate the advantage function for all these actions. And the way I'm going to calculate the advantage function is, first I'm going to estimate the q values for all of this. So this is q pi of s comma a1. This is q pi of s comma a2. This is q pi of s comma a3. And this is q pi of s comma a4. And then I can also estimate v of s. So what is v of s? V of s is the expected return which I get starting from that state till the end of the episode. And let's say we measure this for all the possible states. And we get a value of 35 minus 10 and minus 2. So what does this mean? So positive values mean that that specific action has a positive advantage, which means that that action is better than the policy's default behavior. So action A1 and A2 are better than the policy's default behavior, and action A3 and A4 are worse than the policy's default behavior. This is what the advantage function intuitively captures. And we have been doing this actually, if you remember dynamic programming. In dynamic programming, remember what we did? We initially predicted the value function for a specific policy, and then we checked, is there any action for which q value is greater than the value function? If that action exists, we modified the policy such that that action is taken whenever that state is encountered next. So we were doing something similar to advantage. We are trying to say that in dynamic programming, first you calculate the value function using a given policy, then you try to find actions which give a positive advantage. If you find that there are actions with positive advantage, it means that there is still scope for improvement. And then you improve your policy. But if all advantages are negative, it means that your current policy is completely optimal. So advantage also gives you a perspective on whether there is a scope for improvement or your current policy itself is completely optimal or not. That's why people prefer a lot to work with advantage function, because instead of uh, calculating these two values separately, you can just use a simple terminology called advantage, which also offers a nice intuition. And now you can probably understand why this comes in this reinforce with this intuition. If you replace with a, it makes sense, because if my action has a positive advantage, I'm going to increase the probability of taking that action. If my action has a negative advantage, I'm going to decrease the probability of selecting that action. So action advantage makes a lot of sense when applied in the reinforce algorithm as well. Now the question is that how do I estimate these advantage functions? And because they are central whenever we are going to use policy gradient algorithms in the future also, we need to find a way to estimate these advantages. And let us try to understand how we can go ahead and estimate the advantages. So first we are going to look at the formula itself, which is q pi minus v pi. Now what we do is we expand this q pi and we write it as expectation of RT plus gamma RT plus 1 plus gamma square RT plus 2, etc. dot dot dot. Then we write this at RT plus gamma times everything inside, which is RT plus 1 plus gamma times RT plus 2 plus dot dot dot. So this also can be written as RT plus gamma times expectation of everything inside. And this is nothing but value function of state ST plus 1. So essentially, the expected value of q pi is also same as the expected value of the immediate reward plus gamma times the value function of the next state. And if you remember, this was exactly the same as the temporal difference target. Some of these things I think some of you might have forgotten, so please revise the lecture number 2, where we have specifically looked at this same temporal difference target. So now you can use RT plus gamma times value function of ST plus 1 as a proxy for Q pi. Okay, so you can basically write down the advantage as something like this. The advantage or the estimated advantage is equal to RT plus gamma times value function of the next state minus V pi. So you can write it like this. So this is also called as a one-step backup, because we are using the value function of the next state to estimate uh, the Q value. Now you can immediately see the benefit of this. One of the benefit is that you have expressed everything in terms of the value function. So you have removed the Q from the equation completely. And this is fine. You can actually use this as an estimate directly for the advantage. But people ask this question that why do you only use a one-step backup? Why not use a two-step backup or a three-step backup or a four-step backup? So the natural question is that can we look, let's say, two steps ahead? So if we consider a two-step backup, the Q estimate becomes this: RT plus gamma times RT plus 1 plus gamma square times V pi of ST plus 2. Now remember, our previous Q estimate was only the first two terms, which is RT plus gamma times RT plus 1. But right now we have added a third term also here, because we are looking two steps ahead. Now the advantage function can be written as RT plus gamma times RT plus 1 plus gamma square times value function of the next to next state, which is two times ahead, minus value function of the current state. This is anyways coming from the original formula itself. Okay, so now this is fine. So can we do an n step backup if n is very large? Can we do a 3-step, 4-step, 5-step backup? So the diagram looks something like this. One step backup is we use the temporal difference target as the Q value approximation. And for a very high step backup in which we use all the states in the episode, it simply becomes a Monte Carlo target because we are adding up all the returns from the start state to the end state. So we can think of this as a one step backup, two step backup, three step backup, or an n step backup. Okay, so now there are multiple ways of doing this. So the question is that how we are going to use a combination of these ways to find the advantage. So then what people said is that can we, let's say, do something like half of a one step backup and half of a two step backup, let's say. So then the Q estimate would look like half into this one step backup plus half into this two step backup. And then the advantage estimate would look like this. This is the half plus one step plus half of two step backup minus the V pi. And the backup diagram is given like this, half and half, you combine it together. So more generally, in a more complex backup, what people do is that they assign a weightage of 1 minus lambda to the first step backup, then 1 minus lambda times lambda to the second step backup, and similarly 1 minus lambda times lambda square to the three step backup, and like that they go on. And this is the last step backup, which is lambda raised to t minus 1. Now, I'm going to explain this again, so don't worry if you are finding this too complex. But why this lambda is introduced? Imagine now if lambda is equal to 1. What will happen if lambda is equal to 1? This is 0, this is 0, this is 0. So you are only considering a n step backup, which is the Monte Carlo target. And if lambda is equal to 0, then all of these are 0. And you are only considering a one step backup, which is the temporal difference target. So lambda is like a knob which you can tune to either focus on just one step, or if you want to focus completely from start to the end of the episode. So now this is how the final formula is given for advantage. 1 minus lambda times one step return plus lambda times 1 minus lambda two step return dot 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 till the lambda raised to n minus 1 1 minus lambda n step return minus v pi of st. And if lambda is 0, then we are considering only the first step. So the variance is going to be low. If lambda is going to be 1, then we are adding all the steps. So the variance is going to be high. But the bias is very high in the lambda is equal to 0, because why are we preferring only one step return? Why not other step return? So lambda also can be considered as a knob which controls the compromise between bias and variance. So let me again actually explain this, how advantage is calculated. So a very simple way to calculate advantage is just use a one step return like this. That's it. Just use a one step backup where you replace the Q value estimate by RT plus gamma times V pi of ST plus 1. And this is something you can go ahead with. It is fine. There is no problem, but it has a lot of bias, right? Why do I only look at a one step return? Why can't I look at two step, three step return? So then you try to look at a two-step return, your formula becomes like this. And similarly, then you try to look at an n-step return, which is basically adding up the returns from all the steps, which is similar to Monte Carlo return. And then you think that, okay, fine, now I'm going to do a combination of one step and two step backup, so half and half. But then you say that why half and half? I want to now include all the steps. So you do this where you assign a weightage of 1 minus lambda to one step backup, 1 minus lambda times lambda to two step backup till the last step. So lambda offers you a very nice control between bias and variance, or control between temporal difference or Monte Carlo targets. So in practice, this lambda is also a hyperparameter which is used in the advantage estimation. And finally, to estimate the advantage, all you need is the value function estimation. You don't need anything else. And this method is called generalized advantage estimation, or it's also called GAE, which is the generalized advantage estimation. Yes, someone is asking about the intuition behind bias and variance, and that is a very important concept to understand. So let's take an example where lambda is equal to 0. If lambda is equal to 0, then all these other terms are 0 and we are only focused on this first term, right? And that is highly biased. Why are you focused on term number 1? Why are you not focused on the second step return or third step return? So this is extremely biased. But at the same time, it has a very low variance because I have only one single term to add. So it has high bias, but it has low variance. On the other hand, if I choose lambda equal to 1, then I am essentially focusing on an n step return, which is I am adding the return from all the steps which I am encountering. So in this case, my variance is going to be very high. And why is my variance going to be high? It's because I am looking at n steps. Let's say there are 50 steps in an episode. I am adding 50 different terms, which is going to give rise to a high variance. And there is no question of bias here because I am giving attention to all the steps. I am not just attending to one or two simple steps. So the question is that even n step return will be 0 where lambda is 1. So yeah, that's correct. So for the last step, the formula, the term is actually this lambda raised to t minus 1. So if you substitute lambda equal to 1, everything becomes 0, but the last term does not become 0 because it does not have a 1 minus lambda factor here. It only has a lambda factor here. So that's why the last step does not become 0 for lambda equal to 1. And you end up adding all of this. You end up focusing on all these different steps which you encounter in the episode. So that's why it offers a knob between bias and variance. And typically, I have seen people use lambda between 0.5, 0.7, something like that. Okay, so in today's lecture, we focused on first understanding why do we need policy gradient methods, because it offers a way to bypass the Q function estimation and directly give us the probability distribution over actions. And then we understood, okay, fine, if we want a direct estimation of the probability distribution, we first need to parameterize our policy with a parameter called theta, and theta are nothing but very similar to the weights of the neural network. And to find the theta, we need to first define a performance measure, which was defined as g of theta. And performance measure in our case is the value function of the start state of the episode, which is the expected return my agent is going to get from the start to the end of the episode. So now I have selected my performance measure. Now I need to traverse my performance measure curve so that my policy improves. But that was challenging because it's a difficult mountain to traverse. It's not an easy mountain. But suddenly it became an easy mountain because we had the policy gradient proof. And we could see that the gradient depends on two factors, the gradient of the log probabilities of the actions multiplied by the returns received at every step of the way. And then we said that, okay, now it's possible to estimate the gradient of this measure. So why don't we write down the gradient ascent rule? And then we can solve these problems using the policy gradient method. So that was called as the reinforce algorithm. But the problem with that is it suffers from a very high variance. And to reduce the variance, we introduced a baseline, which we called as B of S. And very often that baseline is the value function. So to understand this effect of baseline and how it reduces variance, we looked at a very simple and a nice example of a CartPole problem, where we learned to balance the CartPole with a reward of more than 500 using both the methods. And we saw that baseline reinforced with baseline converges much faster and the reduce and the variance is also significantly less compared to the reinforced method. And then we again looked back at the entire formulation and we came up with this very nice formulation where we replaced the g of t or the q of t by the advantage function. And the intuition behind the advantage function is that it tells how better or worse the action is compared to the policy's default behavior. And then to estimate this advantage function, we can either look at one step backup, two-step backup, or n-step backup, or we can look at a combination of uh, all of these different step backups. So if it's just a one-step backup, it becomes highly biased. If it's a n-step backup, it becomes highly variant or it has a high variance. So it's better to have lambda value which is between 0 and 1. Okay, so this brings me to the end of today's lecture. Uh, in the next lecture, what we are going to do is that we are going to start looking at uh, LLMs or RL and LLMs intersection, how to model LLMs as reinforcement learning problems, what are states, actions, policies, what are trajectories, how to sample from trajectories, how to perform policy gradients. So next lecture will be an introduction to RL, but from a lens of large language models. And then slowly we'll move towards algorithms like PPO and GRPO, which are going to be crucial for our bootcamp. And we will also implement one RLHF pipeline from scratch so that you will understand how the policy gradient methods are used. Okay, everyone. Thanks, and we'll meet next week. Bye.